So in this problem, we are looking at two masses, two blocks, which are connected through a very ideal pulley and rope system. And we are really just trying to look at the relationship between the two. Now we're going to take a free body diagram of both blocks. And our goal is part A to find the acceleration, A, of the blocks. And we're also trying to find the tension T in the rope and the string. So let's start with block two. Block two is pretty straightforward. We have the force of gravity, and we have tension, T. What is the force of gravity? What is Fg? Remember, it's just mass times gravity. And so for block two, we see that that is 20 kilograms times 9.8. That tells us that the force of gravity is 196 newtons. And we can use the net force in the y direction to be, sorry, that's my bad. We actually don't know what the force of tension is. Right? We can't just say that the net force is equal to 0. We actually have motion, right? These blocks are moving. And so that does kind of complicate our equation to the point where we know that net force equals mass times acceleration. Our net force is going to be T minus G, right? We can sort of call this Fg, and that's going to be 196 newtons. And that's going to be equal to mass times acceleration. So our net force is just the positive tension force T, and then we're going to subtract the downward gravity force, which we calculated as 196. And so we have found, well, let's just add 196 to both sides. Let's say that T is ma plus 196. Let's indicate that this is the mass and acceleration of block 2, just to be very clear. But we actually know that tension in both everywhere, the tension in a single rope is always consistent through the entire rope. Tension can't change. You can't have one segment of rope with a higher tension than the next segment. As long as they're all connected and it's one fluid, straight piece of rope, tension inside it is always constant. So when we look at this block, well, we're going to want to do a free body diagram where we have a force at 40 degrees, and this is our tension. We have force of gravity, and we have the normal force. So we actually can take let's draw that. We can take the net force in the x direction and set that equal to m1, a1, the mass of block 1 times the acceleration of block 1. And the net force in the x direction, well, we know we have t in the positive direction, so positive t, and we're going to subtract the x component of the force of gravity. That should be pointing straight down. It's a little bit crooked, like straight down. So we're subtracting the x component. So remember, we're taking the magnitude, 196. Oh, sorry. We'll just call it Fg. This mass is a little bit lighter, right? This is a 15 kilogram block, so it's not the same force of gravity. This is a lighter block, so the force of gravity is going to be different. Remember, we are taking the x component. That's the opposite side. So that means we are using sine of 40. And that is equal to m1, a1. And we can use the Fg equals mg equation to say that T equals m1, a1 plus Fg sine 40. Just moving that term over. And then we are going to evaluate sort of Fg, right? 15 times 9.8, 9.8 times sine of 40. Now, we actually know that T is this number, this sort of M2A2 plus 196. So we can combine both of these equations and we can set them equal to each other. M2A2 plus 196 equals M1A1 plus, and we're going to put that last little term into the calculator just because it is so long. And that whole thing goes to 94.5. A little bit of rounding there. And we can, well, let's try and figure this out. We have actually four variables here. M1, M2, A1, A2. So let's see what we know. Well, we know the mass of 1 and the mass of 2, right? M2 is 20 times A2 plus 196. And then the mass of 1 was 15 kilograms times A1 plus 94.5. Now we have A1 and A2, and that's all we're left with. But that's two variables. And that can be, we can't solve it with one equation. We need a new second equation, a new equation. And that's what's going to help us sort of unlock this problem, right? We know that these two blocks are connected by rope and are moving together. And if you think about it, what can we say about their relative accelerations? We can say they're the same, they're equal. A2 equals A1, and we'll just give it some new letter, just plain A. They have to accelerate together since they are connected, right? The rate at which 2 accelerates is the same as 1 because the rope is always in tension, right? Because the rope is always in tension, we know that they move together. That rope is never going to become slack, which might mean that they're not moving together. We know it's always a taut rope, right? Because of the situation, this problem. We know that they have to move together. And so in any kind of problem where we are given like this picture of two blocks, one sort of hanging down freely, one going down an incline, most of the time we're going to notice that their accelerations are the same. As such, we have 20a plus 196 equals 15a plus 94.5. And so the last thing to do here is to go through and do some algebra. We're going to subtract 94.5 from both sides. And so we'll also subtract 15a from both sides. Minus 15a. We get 5a plus 101.5 equals 0. And a equals negative 101.5 divided by 5. That gives us 20.3 meters per second squared. Now, we got a negative. So let's make sure we keep that there. Because that negative tells us that we are accelerating sort of downwards in the negative y direction. The negative is a little bit confusing, right? It's a little weird. Not exactly what we would have expected. But we know that there's only one way for this system to accelerate, right? Block 2 has to go down. Block 1 is not going to be pulling block 2 up unless it is considerably more mass. And it's actually lighter. Block 2 is going to have a much larger pull, and we see that block 2 goes down. This is its acceleration, and the tension in the string, whoops. Well, we can go back to one of our equations, say this one for, let's do, yeah, right here, this one. T equals M1, 15 kilograms, times acceleration of 1, 20.3, plus 15 times 9.8 times sine 40. We found that to be 94.5, so we're just going to use that number. And we can find the tension in the rope. And that's going to be 399 newtons. And that is the tension in the rope.